Uh, Allison Moore from Virginia Commonwealth. Yeah, I read Texas Christian there. She's going to speak on not Floer homology and Conway spheres.
Thank you so much to the organizers for giving me the opportunity to tell you about this project. Everything that I say is going to be joint work with Ty Lidman, who is at NC State University, and Claudius Zibrowius, who is at the University of Regensburg. So this is a project that is about Dehn surgery, essentially, and some other things as well. Dehn surgery is a fundamental cut and paste operation by which you take a knot or a link and use it to construct some kind of three manifold. So roughly what you do when you're doing Dehn surgery is you take your knot in the three sphere and you remove a tubular neighborhood of that knot, and then you're going to glue in a solid torus. You're going to glue it by some map H that's going to take a meridian of that solid torus and then identify it to a rational slope on the boundary of what you cut out. So you choose some sort of basis, M and L, and then send the meridian to PM plus QL. And that's PQ Dehn surgery. There's lots of familiar examples that I could mention, so let me just doodle a couple of them. If we take an unknot and we do P over Q surgery along this unknot, that's going to produce the Lspace LPQ, or maybe minus LPQ, depending on your sign conventions. Let me take not a knot, but instead a link. Let me draw the Whitehead link. So this is a link with two components. I could do +1 surgery on one component and -1 surgery on the other component. And that is going to give me a Brieskorn sphere, sigma 237. Or maybe I don't want to do -1 surgery, I take +1 surgery and +1 surgery. If I do that instead, I'll get the Poincare homology sphere. All right, so some common three manifolds. So Dehn surgery is extremely useful and extremely widespread, and it's good for homological calculations if you want to do the Meyer-Vietoris sequence or something like that, but it's also universal. There's a theorem due to Licorice and independently Wallace from 1960 and 1962 that says every closed-oriented three manifold can be obtained by doing Dehn surgery along, if not a knot, then a link of some number of components. So there's various natural questions that arise if you're considering Dehn surgery. First, when is a three manifold realizable as surgery? We know it's realizable by surgery on a link, but when is it realizable by surgery on a knot? Or maybe you just want to bound the number of components of your link and say maybe a link of at most 2 or 3 components. So this is a type of question that you can ask. And there's a lot of different ways to approach this question. And Floer homology, which is something I'm going to talk about in a few minutes, has been very good at answering this type of question. Another related question is, given your favorite type of three manifold, whatever that is, try to classify the knots or links that can be used to construct it. And short of doing that, maybe you could produce some obstructions instead. So these questions are actually pretty hard. And to illustrate their difficulty, in many ways, Lspaces are the simplest types of three manifolds. They have finite fundamental group and they're Dehn surgery on an unknot. But we still don't yet know which knots have Lspace surgeries. There is a list due to Berge, but it is still conjectural. So even in the case of Lspaces, these are pretty hard questions. Or at least number 2 is a pretty hard question. So maybe we're going to go down the route of coming up with an obstruction instead. So sometimes essential surfaces in the complement of the knot can be used to give you some insight or provide an obstruction if you're thinking about these kinds of questions. So I'm going to draw an example of some knot. So let's take a pretzel knot. This is going to be the -2, 3, 3, 3 pretzel knot. The number of twists in these regions is not important, but what matters for this example is that I have 1, 2, 3, 4 different twist regions in this pretzel knot. Say this is my knot K. So let me form a closed oriented surface in the complement of this knot by taking a sphere this blue sphere. This sphere is going to not be in the complement of the knot yet because it's intersecting the knot in 4 points. And let me add some tubes. I'm going to add a tube along one of the strands on the outside in purple, and then another tube in green. And abstractly, what I have now is a genus 2 surface. So this is my closed surface, which is incompressible in the complement of this knot. And it's a result, I think, due to Ortel, or maybe somebody can later correct me on this, but Ortel in 1984, that this example, amongst other related examples of this closed incompressible surface, is going to remain incompressible after doing Dehn surgery along K. So I'll just say here, this surface F is incompressible after surgery. And the thing about incompressible oriented surfaces is that they're pi1 injective. So what that would tell you is that the fundamental group of Dehn surgery is infinite. For non-trivial surgery. So this is surgery along this knot is not going to give you, say, a Lspace, if that's what you're interested in. And by the way, the sphere that we drew here is an example of a Conway sphere. So let's say a little bit about Conway spheres too, because that's going to be a particular interest to what the result I want to tell you about. So Conway sphere is, it's a sphere that intersects your knot transversely in 4 points. And like what we drew before, and they give rise to tangle decompositions. So I can write S3 as the union of two balls, and inside each one of them is a pair of properly embedded arcs. You could also consider tangles in more components, but I'm just considering 2 properly embedded arcs. So I have a tangle decomposition of this particular knot. Here's a tangle, say T, and here's another tangle T prime. This is not an essential tangle decomposition, by the way, because the tangle that I see on the inside is just a rational tangle. I'll say more about that in a second. Yes, so what does it mean to be essential? It means that that sphere, minus the punctures, is incompressible in the complement of the knot. So it's pi1 injective, or alternatively, you could say that it's incompressible on both sides. And rational tangles have compressing disks. That's an important example. So I have drawn here a rational tangle and something that's not rational. So I should probably clarify, come back to this example. So the easiest rational tangle to draw is the trivial one. And you can see you're separating compressing disk here that separates the 2 trivial arcs. And you can act on it with like the mapping class group to twist it up to get a generic kind of rational tangle. So these are going to be inessential. And then a different type of tangle will be something like what I just erased. So this is not a rational tangle. I have here a tangle sum, basically, of 2 rational tangles, but together it's not rational and there's no compressing disk in there. And so that's a little bit about tangles. All right, and if anybody, it's the last talk of the day, so if anybody has any questions, please just unmute yourself and ask. I don't mind being interrupted. So let me mention now a result that is due to Wu. So I'm not stating it as a theorem because this result is implicit in his work, but you can find it in work of Wu from 1996 that if K has an essential Conway sphere in its complement, then if you do non-trivial Dehn surgery along K, that manifold will have infinite fundamental group. I see now that I left that out of the statement right here. There should be an is infinite here. Yeah. So that is due to Wu. And so what we are going to prove is a generalization of this result. So our main theorem says that if K has an essential Conway sphere, then Dehn surgery along K will never be an Lspace. Haven't defined what an Lspace is, but I will in a moment. An Lspace basically is a kind of Haggard Floer version of a Lspace. But there's a fact that's relevant here, which I'll just jot down. And that fact is that every closed oriented three manifold with finite fundamental group is an Lspace. And as a consequence, we get Wu's result as an immediate corollary. Because if the fundamental group were finite, then it would be an Lspace, and that would contradict our result. Okay, so this is the main thing that I want to tell you about. I'm going to tell you a little bit about the techniques and the tools that we use for proving it. Okay. So let me say some words about Hagarclermology and not Floerology. So Hagarclermology is due to Oshkosh and Szabo. This is a package of three manifold and four manifold invariants. And there is a refinement of this theory for knots that is independently due to Rasmussen. This theory's been around for about 20 years now. There's lots of different versions of it, but in one of the simpler versions, you have a knot in the free sphere, and associated to it is a bigraded vector space, which we call HFK hat, Hagarclermology for knots. So it looks like this. You have a finite number of abelian groups. I'm taking my field here to be just like Z mod 2Z. And there's two gradings associated with them, M and A, called the Maslov and Alexander gradings. So a concrete example would be if I took the knot 5-2, which is what's pictured here. This is not a minimal crossing diagram of this knot, but it's a tangle decomposition that I want to use in a few minutes. So it has a few too many crossings, but you could isotope it into a standard picture of 5-2. And if you calculate its knot formology by some mysterious procedure that I'm not yet explaining, you will get you'll get something that is rank 7. So we should jot that down because we're going to use it again. Split into three bigradings, Alexander grading and Maslov grading. So it is symmetric in the Alexander grading and not symmetric in the Maslov grading. Rank 2, rank 3, rank 2. Not Floerology is a filtered version of Hagarclermology for the free sphere. And in the context of three manifolds, you say that a three manifold, particularly a rational homology sphere, is an Lspace whenever it has the simplest possible Hagarclermology. So there's various ways that you can state that. You could say that the rank of its Haggard-Floer groups agree with the order of its first homology. Or equivalently, if you're using the plus or minus version of Hagarclermology, which is a module rather than just a bigraded vector space, it's a module. You could say that it's torsion free as an epijoining module. So there's several examples of L spaces I should write down. The three sphere and all lens spaces. The fact I mentioned a moment ago told us that if you have finite fundamental group, then you're going to be an L space. So anything like an L space, like a lens space with finite fundamental group, but there's also three manifolds that have infinite fundamental group that are L spaces. So it's a larger class than just finite manifolds. Okay. So Lspace knots are knots that have a Dehn surgery that gives you an Lspace. And there is a established and deep relationship between the knot Floerology of those knots and the Haggard Floerology of the manifold that you get from doing surgery. Those groups inform each other and are closely related. Knot Floerology, Lspace knots are also knots that have very special knot Floerology. So there's constraints on their rank. The grading information is highly constrained. And so one thing that you might observe if you look at those gradings is that the kind of difference in one grading determines the difference in the other grading, which is kind of a sloppy way to state this next lemma. So one thing that goes into what we eventually prove is some technical information about the gradings of knot Floerology. There's a lemma that is due to Oshkosh and Szabo in one direction, and then we proved it in the other direction. That says basically, if you're an Lspace knot, then the structure of your knot Floerology groups look like everything is rank 1 in the different bigradings, and you have a strict total order on these bigradings. So you have increasing Maslov gratings with increasing Alexander gratings. This is what it looks like if you're an Lspace knot, and also if it appears in this structure, then that corresponding knot actually does have a surgery to an Lspace. So this is a bit of a technical lemma, so I don't want to say too much about the proof of it. Other than that, it uses the total differential on knot formology and the gratings and things like that. And it's something that we need in order to get at our main result, which has to do with Conway spheres. So what is the proof idea for the main result? Well, we're going to use a different version of Hagarclermology. And it is a version of fluorology for tangles that is due to Zibrowius. So associated to a tangle, we have a type of bordered fluorology called a peculiar module. Right, I'm going to borrow a graphic from here on my other slide, so I don't have to draw this. Put it here. So, and I'm going to make it small because I just kind of want to talk about it. But you take a tangle like this, and then you associate to it some sort of module. Also, you could think of it as a type D structure if you're familiar with bordered fluorology. And then this module has a geometric realization as, in this case, an immersed curve on the four-punctured sphere, or in general, a set of immersed curves on the four-punctured sphere. So when you have a slightly more complicated tangle like this one, this is one of the tangles that appeared in that drawing of 5-2. The geometric realization of this algebraic object looks like a set of three curves. There's one at the top, there's one with a dashed line, and then there's one at the bottom. It's decorated in the sense that you have to record the grading information of Hagarclermology somehow. So it's decorated with Maslov and Alexander gratings, or the delta grading, which is a linear combination of the other two. And there's also something called local systems involved, which I don't want to say too much about, but are basically invertible matrices. All right, so there's a lot of structure to this invariant that's good for using. And let's see, what are the most relevant parts of the structure to tell you about? Well, these curves fall into two categories, rational and what we call special. Rational components are the components of rational tangles, and special components are something that is actually immersed rather than embedded. It's a result of Zibrowius that a tangle is rational if and only if you have a single embedded curve. If you have something which is not rational, it can have these embedded curves appearing as part of its sum ends, though. The immersed components, which are what are pictured here at the top and at the bottom, appear in conjugate pairs. And another little detail that we proved in the course of going through our main result was that the number of rational components has to be odd. So there's some interesting combinatorial information that you can use when you're looking at this invariant. All right, so the most useful piece of information about this Tangle invariant is that you can do Hagarclermology by doing Lagrangian intersection homology. So what you have is a tangle decomposition like this. So I have written 5-2 in a slightly inefficient way because I need to glue these tangles together in a kind of prescribed manner. So I have a tangle and I have another tangle. I've kind of moved this rightmost tangle around in this picture, so sorry about that. This is all 5-2. And this set of three immersed curves over here is the tangle invariant that realizes the bordered fluorology of this tangle. The red curve I've drawn separately, and that's the tangle invariant. It's a single embedded curve for this simple tangle that has one crossing in it. So if I want to calculate the Hagarclermology of the knot 5-2, then I'm going to take the intersection homology of these two sets of immersed curves. So what I can actually do is superimpose the red curve on top of the blue curve and just count intersection points, because every bygone in this picture has a base point in it and it's not going to be counted by the differential. So I can do that right now and calculate at least an ungraded version of Hagarclermology because I don't have the decorations for gradings in this picture. So I should superimpose red over blue. Let me make sure I have only regular immersion points. Okay, and let me count intersections here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Now I've done something wrong. Yeah. 1, 2, 3, 4, 5, 6. I have some, I think I need to isotope this a bit. Let's start over. It should be the minimal intersection number. Let's try again. Oh, I know, I'm circling the wrong punctures. That's the problem. Okay, 14. I counted 14 points when I did it correctly. All right, good. So what this theorem says is that I have the Haggard fluorology tensor V, which is a two-dimensional vector space, giving me this intersection homology. So because I had 14 intersection points, this rank was equal to 14. I divide by 2 and I get 7. And 7 was the dimension of 5, 2. So at least we got it to agree on rank. Right. So this is a very handy way of calculating that formology. Yeah. All right, so I'll just say 1 or 2 more words about the theorem statement. So this is the general invariant that we're going to use is this Tangle homology. And we have to prove something to use, and that is that that the Tangle invariant detects split knots and links, split links. So what we say is that H of T contains only embedded curves that are all of the same slope if and only if the tangle is split. So it's another kind of structural result about the Tangle invariant. And by a split tangle, what I mean is it could be like a rational tangle, but you could tie a knot into one of the strands, but there's still a compressing disk that you can find for that tangle. So rational tangles and tangles that have knots tied into the strands. This type of result uses a little bit of sutured formology. And then the outline of the main result, which I've restated here. Okay, so we have K, and we're assuming that it has an essential Conway sphere. And we want to show that Dehn surgery along this knot is never an Lspace. Well, assume that you have a tangle decomposition using some essential Conway sphere. Neither one of these tangles, T1 nor T2, is split because this is a Conway sphere, an essential Conway sphere. And due to some of these structural statements, the Tangle invariant for each of these tangles has to contain a lot of different curves. It's either going to contain immersed curves that occur in pairs, or it's going to contain multiple embedded curves of different slopes, or it could contain both. And because of this, there's a lot of different curves in the invariant. And so when you go to calculate the intersection homology, there's a lot of intersection points. So the Lagrangian Floer homology is complicated. So in some cases, rank is enough. It's enough to say, well, I go to calculate the knot Floer homology in some particular grading. The rank is greater than 1. And based on my rank requirements for Lspace knots, I've exceeded rank 1, so that can't happen. But it's not enough to just consider rank. We also have to consider the grading structure, which is the reason why we have these technical lemmas that say the gradings have to behave in these very constrained ways when you have an Lspace knot. So with a combination of rank and grading, we can calculate this intersection homology to calculate the knot Floer homology. And we do it pairwise. So for example, in the knot 5-2, when I did this count, at least when I got around to doing it correctly, I'm counting intersection points between red and blue, but also red and dashed blue. So I can take them separately and then add up that intersection number. So often what we have to do in our proof is actually calculate things pairwise. And then each one of these has to assemble into something that overall has the structure of an Lspace knot. So we would have some chunk of generators coming from a pair of curves and then another chunk coming from another pair of curves. And if they overlapped in some kind of Alexander grading, then that would be bad. And that's kind of the general idea. So I think this is probably the right place for me to stop and to thank you all for your attention today.
Thank you. Are there questions for the speaker? No? Okay, well, let's thank the speaker. And I think that's the